Good morning. So, in the last few lectures, we had seen about electronic instrumentation, and we had seen how to measure voltage, current, and resistance through different devices. Okay. However, we have also seen that all these measurement devices, they most of them had this problem of being sensitive to environment. Okay, and what do you mean by sensitive environment? Mostly temperature sensitivity. Okay, so as the temperature changes, the internal resistance of the meters can change, and that can affect the reading. Okay, so basically you have some temperature dependence for the reading, and that may cause some error in the reading. Okay, and so the way out of this, particularly when you are trying to measure passive circuits like resistance, inductance or capacitance, is to depend on bridge circuit which offer better accuracy in measurements. Okay, so as I said, the bridge circuits can be used for more precise measurement of resistance, capacitance, and inductance. And it is typically bridge circuits are used where the transduce where the impedance of the elements gets changed due to the measuring due to the measured quantity. So typically we are talking about bridge circuits being used as a sub circuit in a transducer that measures a non-electrical quantity, and the output is a voltage, an electrical voltage. Okay, so an example is like the application in an RTD. So an RTD, or a resistance temperature detector, is basically a resistor whose resistance varies linearly with temperature. Okay, something like the resistance R is some R0 into 1 plus alpha times the change in temperature. Okay, so and this alpha is a very small quantity, so the variation temperature is very small. So to capture the variation in the temperature, we should be able to measure the resistance of the RTD very precisely. Okay, and the bridge circuits can be utilized for this purpose. And similarly, you can have strain gauges which measure strain. You can have capacitance based force transducers like that you have in your touch screens. Okay, so that can be used to precisely, bridge circuits can be used to using such devices, and they can very precisely measure the passive quantity like resistance, capacitance or inductance. Okay. So in this lectures, we'll start focusing on resistance. Okay, and one more advantage of the bridge circuit is that due to the external effects like temperature change or improper shielding or grounding, okay, those effects are nullified because different components of the bridge circuits are affected by these are affected by these external factors in the same manner. So overall, the reading that you take out is unaffected by these external factors. Okay, so as I said earlier, in this particular lecture, we'll be considering DC bridge circuits, that is resistance measurement. So for resistance measurement, we have various configurations depending upon the range of the resistance. So for very low resistance measurements, you have Kelvin bridge circuits, and for very high resistance measurement, you have guarded Wheatstone bridge or Megger circuits, and for medium level resistances, you have the standard Wheatstone bridge circuits. So as Wheatstone bridge is the simplest circuit based on which all the AC and DC bridges concepts would be based on, we'll first look into the Wheatstone bridge and also the analysis of the Wheatstone bridge sensitivity. Okay, now let's refresh the concepts of a basic bridge circuit. So in a bridge, in the bridge circuit, you have a bridge which has 4 arms, and there is a detector connected across the arms. And 2 of these arms are kept fixed, their impedance has not changed. One of these arms would be variable, and the fourth arm and the unknown component that is to be measured is typically kept in the fourth arm. So for example, you can have Z1 and Z2 being fixed, Z3 being variable, and Z2 Z4 being unknown. Okay, and in different bit circuits, the unknown arm and the variable arm are changed. Probably in some cases the variable arm can be spread over two different arms also. Okay, so that we'll come to those peculiarities later. So for now, let's stick to the factor that 2 of the arms are fixed, one is variable, and the fourth has the component to be measured. Okay, now and the variable component, now in this case Z3, is now varied until the detector shows a zero deflection. So when this is happening, you would have the relationship that Z1 by Z3 is Z2 by Z4, or Z1 by Z2 is Z3 by Z4. Okay, in both the relationship could be used depending whichever suits better, that would be used. And since the detector is actually a current measuring device and its deflection is proportional to the voltage drop across these terminals 1 and 1 dash, okay, then the detector sensitivity can be increased, or the accuracy can be increased by increasing the supply voltage. So that is one way that you can increase the effectiveness of a bridge circuit. Okay, but that's not the only way. That's the most obvious way only. Okay, now in a Wheatstone's bridge, all the 4 components, all the 4 impedances are plain resistors, and you have R1 and R2 being fixed. R3 is a standard arm, okay, which has a variable resistance, and the unknown resistance R4 is to be measured. Okay, now as we said earlier that R4 is Rx, and if this bridge is brought to balance, then Rx would be equal to R2 by R1 times the value of R3 at balance. Okay, and once if you have, so now if you change from, for Rx is R4 plus delta Rx, and R3 goes from R3 balance value to this plus delta R3, these two variations, delta Rx and delta R3. So what I say is that if it is balanced with the unknown resistance being R4 and the meter resistance being R3 some balance value, then we can say that by changing R4 to R4 plus R, the unknown resistance R2, Rx is R4 plus delta Rx, then the deflection, or not the deflection, the variation in R3 the adjustment in R3, the delta R3 that is required to restore the balance is also linearly proportional to the change in unknown resistance. So this seems very convenient in sort of making very precise measurements also. So the reason is that we can have the unknown resistance, okay, or the unknown resistance actually being only a part of the what do you call, of the of this R4 branch, or similarly the standard arm, the variable part can also be only a part of R3. So for example, if you have, let us say, a say a 1000 or a 1 kilo ohm resistance, and this is in series with a 10 ohm variable resistance, so we are able to precisely measure from 1000 to 1001 volt, 1001 ohm. That is a variation that we have here, and we are not using a single variable resistance here. You are adding a small range variable resistance to a large range value, and this can be used if you know in the situation that your R4 sort of varies from 1000 to say 1010 ohms. So there is a 10 ohm resistance variation. There is only a 1% variation in R4, but I want to precisely capture that, and that can be captured in this manner. Okay, hope that clarifies that aspect of how the unknown resistance or the standard arm can be modified in a manner that the maximum advantage of the sensitivity can be achieved or can be taken. Okay, and just so that to protect the detector, that is the galvanometer, we should ensure that a large current doesn't flow through the galvanometer. So we would bring R3 to be very close to this value, such that R3 is approximately R1 by R2 times R4, okay, the expected value of R4, and only then the galvanometer circuit is closed. Okay, so to protect the galvanometer, the shunt is used to bypass the meter current till the near equilibrium value is achieved. Okay, now let's go to the sensitivity analysis. What values of R1, R2, the fixed arms, are going to give me better sensitivity, and at what value of so what is the relationship between R1, R2, R3 and R4 that will ensure that I have maximum sensitivity. I am able to detect delta R4 very efficiently. Okay, so in the bridge circuit, the important aspect is how close to the null value can I find a detection. Okay, how closely the null deflection or an imbalance can be detected. So we want to get the point where R1 by R2 is R3 by R4. Okay, however, how do we know that this point is achieved? This we can only know if we can know that R1 by R2 not equal to R3 by R4 is detected. So how close is this detected? How close to the equality but being unequal can we go and still detect a deflection? Okay, and that is basically, in plain words, that is the sensitivity. Okay, however, plain words is not enough. We have to go into the mathematics of it. Okay, now let us assume that the circuit is initially as a balance and the unknown resistance changes from R4 to R4 plus delta R4. Okay, so to get it back to balance, so this would mean that there is a potential difference between the points R and S. Okay. Now, if the galvanometer points are opened, okay, this ERS would be ERQ minus ESQ. Okay, or that can be written in this manner. It can be simplified, and you will get ERS to be this expression. Okay. However, this expression seems a little complicated. However, there is a way to simplify this. Okay. Note that at balance, you had R1 by R1 plus R3 is R2 by R2 plus R4. Okay. At balance, basically what you had was that R1 by R2 is R3 by R4. Okay, or R1 by R3 is R2 by R4. Okay, you can take it in a different manner anyway. Okay, now this would mean that R1 by R1 plus R3 is R2 by R2 plus R4. Okay, so we can substitute R1 by R1 plus R3 by R2 by R2 plus R4. Okay, and let's do that. Okay, so which would mean that ERS, the potential difference between these 2 points, can be written in this manner using this expression. Okay, which by dividing the entire expression by R2 by R2 plus R4, dividing and multiplying, taking this common, taking this factor common, you can write it in this manner. Okay. You have 1 by 1 plus delta R4 by R2 plus R4, but what you have is delta R4 is much less than this value R2 plus R4. Okay. Now, under that assumption that the variation is low, you can approximate 1 by what you're using is 1 by 1 plus some delta is equal to 1 minus delta. So you get this expression. Okay, which eventually gives ERS to be given by minus E times R2 delta R4 by R2 plus R4 the whole square. Okay, so this is what we have. Now, if we assume that the voltage sensitivity of this galvanometer that is being connected here, okay, is going to be SV. Okay, then the deflection theta would be SV times the total voltage, the voltage sensitivity. This is the voltage sensitivity times the voltage, okay, which is given by this expression now. Okay, and the bridge sensitivity is the deflection to the deflection in the resistance. So what you have is theta had gone from 0 to some value of theta, and R4 had the unknown resistance had got from R4 to R4 plus delta R4. So your bridge sensitivity is theta by delta R4 by R4. Okay, and if you simplify it, you end up with this expression. Okay, 1 by R2 by R4 plus R4 by R2. Okay, now this expression, the denominator, okay, is minimum when R4 is equal to R2. Okay, you can check out that it's like saying that it is 1 by x plus 1 by x plus 2, the minimum value of this for x greater than 0. Okay, this will be achieved as x equal to 1, and that is R4 equal to R2. So in conclusion, we can say that the bridge sensitivity is maximum when you have R4 is equal to R2. So you should choose R2 in a manner so that choose R2 as close to expected value of R4 or Rx. Okay, so choose R2 in the range of R4. so that the bridge sensitivity becomes maximum. Now, the next thing that we want to do is to see how the galvanometer would function, means how the bridge sensitivity can be further analyzed. The galvanometer basically is not a voltmeter. It's a current measuring device. Okay, it's a current sensitive instrument, and its sensitivity is given by in the terms of current, and the current sensitivity of the instrument and the voltage sensitivity of the instrument. In this case, if there is a Thevenin, if there is a voltage ETH across this thing, across the meter, and in Thevenin equivalent resistance RTH for the circuit when seen across the galvanometer, then the voltage sensitivity and current sensitivity are related by this expression, where Rm is the meter resistance. Okay, now let's get into finding the Thevenin voltage and the Thevenin resistance of the bridge circuit. Okay, to find the Thevenin voltage, it is very simple. You have to find what is ERS, okay, subject to the voltage E, the input voltage E being applied to the circuit. Okay, so it is just, so there are two parallel branches, R1 and R3, and R2 and R4 in series. Okay, and what we want is the voltage here. Okay, and that is quite easy to decipher. It will turn out to be ERS is the same expression, R1 by R1 plus R3 minus R2 by R2 plus R4. Okay, and if the bridge is balanced, this should be 0. Okay, and let's see now, and what we want to see sensitivity around this region. So let us have it as this. Okay, and the Thevenin resistance is given by shorting the input terminals and opening up the galvanometer terminals, so which would be R1 parallel R3 and R2 parallel R4. Okay, given by this expression now. Okay, now at balance, you have the RTH to be this one. Okay, however, if the circuit is if the bridge is at balance, then you already we have seen that R4 by R2 plus R4 should be R3 by R1 plus R3. So the Thevenin resistance can be simplified to R1 plus R2 by R2 plus R4 times R4. Okay, now if R4, if the unknown resistance is changed and the circuit becomes imbalanced, that is R4 goes from R4 to R4 plus R4, delta R4, this we assume that this doesn't significantly change the Thevenin resistance, because from this expression it will come to R1, it will come this in this R4 goes to R4 plus delta R4, and that is not going to be significant change. Probably the change that you have is R2 R4 plus delta R4 by R2 plus R4 plus delta R4, okay, minus R2 R4 by R2 plus R4. Okay, so let's use it in a different sheet. Let me work it out in a different sheet. Okay, so what we had was, we had RTH initially to be R1 R3 by R1 plus R3 plus R2 R4 by R2 plus R4. Okay, and this was taken as R1 plus R2 by R2 plus R4 times R4. Okay, this is at balance. Okay, now if R4 is changed to R4 plus delta R4, so RTH new one will have this one being constant, the same one, R2 into R4 plus delta R4 by R2 plus R4 plus delta R4. Now the change in the Thevenin resistance in both these cases is only can be summarized in this second part itself. So what you have is the change in resistance is R2 times R4 plus delta R4 by R2 plus R4 plus delta R4 Now, if you divide the entire expression by or you take R2, the second part common, so R2 R4 by R2 plus R4 into, so R2 gets cancelled out in the numerator, so I have 1 plus delta R4 by R4. Okay, and here you would have R2 plus R4, so you will have here as 1 plus delta R4 by R2 plus R4, okay, minus 1. Okay, so you would see that delta R4 is getting reduced by such a factor, okay, such that this error is very, very close to 0. Okay, so you can assume that the Thevenin resistance doesn't change significantly. Okay, and even then it doesn't change. It doesn't change even by a factor of delta R4 by R4. It changes by less than that factor, and therefore we can assume that in these two scenarios, the Thevenin resistance remains constant. Okay, you can assume that. Now let's get back to the slide. Now and from that we have the bit sensitivity being determined as R2 R4 by R2 plus R4 the whole square times the Thevenin resistance plus Rm. Okay, how is that? Because I think I have missed one of the points. Because the voltage intensity can be, okay, we can substitute the voltage sensitivity as SI by RTH plus Rm, and you'll get this expression. Okay, so you have the bit sensitivity in terms of the current sensitivity of the galvanometer, the Thevenin resistance, the meter resistance, and the other resistances together. Okay, so let's again see, or let's keep note of what the Thevenin resistance is. R1 plus R by R2 plus R4 times R4, right? So we have RTH is R1 plus R2 by R2 plus R4 times R4. Okay, so we'll make use of that. Let's go ahead. Okay, now as the simplest thing is that the sensitivity can be increased if we assume that the Thevenin resistance is constant, that is R1, R2 are maintained at some standard level, then the sensitivity can be increased by using a more by a larger voltage, okay, or by using a more sensitive meter, that is by decreasing Rm. However, using a more sensitive meter is not going to solve the problem to a larger extent, because RTH plus Rm, if RTH is larger compared to Rm, then RTH plus Rm is only doesn't significantly change the sensitivity. It doesn't significantly change RTH plus Rm, so it is not going to change the sensitivity too much. Okay, so and that is usually the case. Usually you have RTH is much greater than Rm, so the bridge sensitivity will just turn out to be R2 R4 by R2 plus R4 whole square times RTH, and using this expression for RTH, you can get the bridge sensitivity in a simplified manner with this expression. Okay, now we have already seen that the sensitivity is highest near the point where R4 is equal to R2, and then it diminishes in either direction. Okay, now so we have seen that the effect of Rm we have seen, the effect of E we have seen. What is the effect of RTH? Okay. Generally, when you see that RTH is directly proportional to R4, and in a sense directly proportional to the general magnitude. When you say, so what you say is that the ballpark figure of what is R1, R2, R3, okay, the general value or general magnitude of R1, R2, R3 determines the general magnitude of what is RTH. So if these are in kilo ohms, RTH will also be in kilo ohms. If these are in mega ohm, this RTH will also be in mega ohm. So we are not going too specific into that, but that is what is to be seen. Now, if the resistance are modified so that RTH is increased, okay, or decreased. So if you increase RTH, if you use larger value of resistances, the sensitivity will decrease. So large RTH will decrease sensitivity, and you may see that smaller RTH is going to increase sensitivity now. But that sort of exposes a hidden problem, that when RTH is reduced, when the resistance are reduced to a really small value, the way Wheatstone's bridge is connected, it will happen that the resistances of R3, R2 or R4 will become proportional to the resistance of the leads that are connecting different components of the circuit. And now this will lead to significant errors. So if you have R1 is, let us say, 1 ohm resistance, okay, and the lead is itself has a 0.1 ohm resistance, then that would mean that straight away there is a 10% error in the reading, and this may not be acceptable at all. Okay, if the variation itself, if the variation in the resistance is, let us say, 5% due to R4, okay, and you have an inherent error of at least 10% in the bridge itself, that makes the bridge useless. Okay, so when you have too low value of RTH, then this will cause errors to lead resistance, and that makes the Wheatstone bridge useless in those cases. Okay, so that's why the Wheatstone's bridge can be used to measure resistance from few ohms to few mega ohms. Okay, let us say, so if you have 100 ohms to say 10 mega ohm range, in this range you can definitely use the Wheatstone's bridge. For higher ranges you need a different setup. For lower resistance you definitely need a different setup. Okay, because when you have a higher values, instead of the lead resistance being of any significant, the insulators that are used in the system, their resistance becomes of a factor. So if you have a wire in which so if you have the high resistance here, okay, let me draw it properly. Okay, let us say you have a 1 giga ohm resistance, and this resistance is kept in an insulator. Okay, now the resistance of this insulator material will be comparable to the resistance of this giga-ohm resistor. Okay, therefore you need to have circuits that take into account that in fact these high resistances will be 3-terminal or 4-terminal resistances. Okay, they'll have more than one terminal, they will have more than two terminals even though they are resistors, and you have to incorporate circuits which take into account, which incorporate these terminals also, and measure these resistances more precisely. Okay, and so what we have seen is that the Wheatstone switch can be used for from few ohms to few mega ohms. At very large resistance, you have leakage currents that go through the insulator and make it impractical to use Wheatstone's bridge. Okay, and on the other end of the spectrum, when you have very low resistances, you will have high currents, and that can cause heating effects and distort the resistance in the low resistance case. So it can be, Wheatstone's bridge can't be used for low resistance application, really low resistance applications, and we also seen the lead resistances in case of low resistance scenario is also another cause of error. Okay. So we would need significant modification to handle low resistance and high resistance situations. These things we will look in the next few lectures, where the low resistance case and the high resistance case are handled separately by modifying the circuit, modifying the Wheatstone's bridge appropriately. Okay, and these two are the references that you can look into to have a better understanding of this topic. Okay, so with that we come to the end of this lecture. Thank you for your patience.